Welcome to the Soil Moisture Network Operators Workshop. This is March 8th. We have a two-day workshop, March 8th and 10th. And I'm going to talk about East Coast times. Please adjust as possible to your local, but that's what these times are actually referring to. We're setting up our sessions in, let me see if I can, we have two main formats. We'll be doing presentation discussion and breakout discussions. We have each of our hour-long segments really broken into 50 minutes and a 10-minute break at the end, so everybody can get up and bio break. Presentation discussions, we'll start out with a few presentations that are short, we hope, 8 to 10 minutes apiece, and then we'll go into as much as possible interactive discussion across the group, the entire group, in this case being 82 people. To really have everybody exposed to the same information. During the breakout discussions, we have three of those across the 2 days. That'll be smaller groups, and we'll have more interaction and discussion there. So everybody gets a chance to talk, but we're hoping that everybody will either have a chance to communicate in the chat room or talk live. We'll use the raise your hand chat to try and minimize talk over discussion between folks, but that is how we'll work this. The idea here is this is a network operators workshop. It's really for the network operators to communicate with each other and share information, share knowledge, and create a community of operators who can help each other out. Sometimes you might find yourself asking the question, oh man, if I just knew how to solve this problem while I'm out in the field. Well, wait a minute, Kevin has a network that similar to mine, and he had some way to solve this. Let me give him an email, let me give him a call. And that's what we're hoping to establish with this community. The workshop was actually, I didn't pick Kevin out of a hat. Kevin Hyde is from University of Montana, and Montana Mesonet suggested the organization of the workshop to really have boots on the ground folks talk to each other. And he came to us at the National Coordinated Soil Moisture Monitoring Network, which is a community of people, really, at this point, trying to work towards a cohesive soil moisture strategy across the US. So we started a couple of years ago. We've had a loose community for many years, but we got a little more organized in about 2018. We started writing a strategy document that was at the request of NIDIS in Congress. To document and form a way of organizing soil moisture resources in the US, not by running them or managing them, but to improve communication between those networks and strategize how could build out occur when new resources become available. Perfect case in point is the Upper Missouri River Basin that was funding sent to US Army Corps of Engineers to improve monitoring in the Northern Plains. So this doesn't come without, it's not pie in the sky, this will never happen. There actually has been action happening, and we just like to have some cohesive strategy to have this effort be fully informed as it's going forward. So we're going to start with a few presentations on networks of different scales and origins, so that we have an idea and a reference point for all of our discussions going forward. So with that, I'm going to start with a presentation by Mike Strobel. This is he is the lead at the Northwest National Water and Climate Center in Portland, Oregon. And he will be, is he in the chat? Mike, are you in the chat? There will be several other folks in the chat who deal with SCAN, and we'll try and respond to that. But he's recorded, so while you're listening to him, if you have questions, feel free to post them in the chat, and we'll try and respond as we go. Let me get his presentation going.
SCAN is a nationwide network of soil moisture, soil temperature, and other climate information that is operated through the USDA Natural Resources Conservation Service, really to provide data, to provide information and support for our mission, which is the natural resource assessments, conservation activities, and other areas of focus. But there's other aspects to the SCAN network, because we also provide data that's used for drought mitigation, for what we call precision agriculture, where agricultural practices can be modified, adjusted, and focused based on true scientific information, true data, such as when to irrigate, how much water to use, and other irrigation activities. And then also soil taxonomy, where we uh, do an assessment at each of the sites on a soil profile. So information about the soils at each of our data collection sites. And of course, like with any data collection information that's available, there's also the climate change part of it, information that is utilized by those that do research. The network itself, as I mentioned, is administered by the Natural Resources Conservation Service through our center, the National Water and Climate Center. And we work closely with other parts of our agency, which includes the National Soil Survey Center and the Soil and Plant Science Division. Our focus, because we're part of USDA, is really on agricultural areas. So we collect this information uh, as it relates to agriculture. And as I mentioned before, we have soil temperature and soil moisture, but we also collect information on air temperature, relative humidity, solar radiation, wind speed and direction, precipitation, barometric pressure. The network began as a pilot project back in 1991 with 21 stations located across the country as sort of a proof of concept to see if the instrumentation that we utilize for uh, collecting information with the SNOW network could be used then for areas outside of the Mountain West, could be used in areas for providing a tool for agriculture. And this was expanded to add in some of the watersheds later, and also for classification of soils. And so the original funding for this was through a number of different agencies within USDA, as well as other outside agencies. But interest in this pilot study, interest in SCAN expanded, and the number of stations has grown continuously over the years. As more and more people would like to have SCAN stations associated with their regions or states. And so currently we have 215 stations across. The question comes up often about what are the costs for a SCAN station, and approximately uh, the equipment, the travel, the installation is about $30,000 for each of the SCAN stations. Now, this varies as depending on the location. So if you're located in areas that are more remote, more difficult to travel, more costly to travel, including places like Hawaii, Alaska, the Caribbean, then the cost could be more. And likewise, it could be less if you're in areas of easier access. Now, this also requires an annual maintenance cost. And again, this is an approximation, an average for each site, but about 5,000 a year. We try to visit each site annually, but that's not always the case. But on average, this costs about 5,000 per site for the travel, the sensors, the upgrades, the calibration included with that. The network itself, as I mentioned, is across the United States, as well as Alaska, Hawaii, Puerto Rico, and the Virgin Islands. And as you can see here, with the 215 sites, and they're in 40 different states at the current time, there's certain clusters in areas, such as in Utah, where there's a large concentration, as well as in Mississippi and Alabama. There's areas of clusters of concentrations of data points. This is related to the funding mechanisms. These areas requested these sites. They funded and assisted in the installation of the sites. And so that's why there's some areas that have a different spatial distribution than the rest of the country. The system is set up similar to the SNOW system. We originally used the meteor burst system for the telemetry to transmit information to our office in Portland, Oregon, but currently the network is set up for telemetry with cellular because most of these areas are covered with cell coverage, and areas that don't have cell coverage, we utilize satellite telemetry such as GOES and the Iridium system. This is a typical setup for a scan site. You can see the tower, the boxes where we hold things such as batteries um, and the radio transmitters, etc., other equipment inside the boxes. On the tower itself, you'll see different sensors for precip, wind speed and direction, humidity, solar radiation, etc. And then solar panels are used to charge the batteries which operate the system throughout the year. These scan stations do not tie into any electrical grid. They're self-contained, so everything is on solar panels and that charge up 12 volt. The sensors, the probes that we use for soil moisture and soil temperature are located at 5 depths. The deepest is at 1 meter, and the other ones are set up at 2 inches, 4 inches, 8 inches, 20 inches, and of course the 40 inches is the 1 meter depth. Or if you wish to put it in metric, you're looking at 5, 10, 20, 50, and 100 centimeters in depth. And the sensors collect information continuously. We transmit the information on an hourly basis, so it's in near real time. And this is one of the graphics that come from this. So you can see that on the bottom of the graph is precipitation. And we can see the dynamic characteristics of the shallow soils as they relate to some of these precip events versus a more subdued reaction in some of the deeper soil areas. In addition to the sites that we have on the SCAN network, we also have a number of our SNOWTEL and SNOW light stations in the Mountain West that also have soil moisture and soil temperature. And each year we try to upgrade the number of these sites with these sensors. Currently, right now, there's 464 SNOWTEL and SNOW light stations that have these sensors, soil moisture and soil temperature. So collectively, with the SNOWTEL network, the SNOWLIGHT, and then the SCAN network, we have 679 sites across the country that collect soil moisture and soil temperature in near real time. How do we decide where the sites are going to be located? Obviously, we'd like to have a good spatial distribution, but there are criteria that we look at. One of the first ones is that we want these sites located on federal, state, county, or university lands. And the reason for this is that oftentimes private land ownership changes hands uh, and possibly would not like to have the station located, the new owners would not like to have the station located on their lands. There's security factors as well. So having it on these government properties allows for a longevity of the record. So we want to make sure that we can continue to have a long current record at each of the sites. We look for areas that are non-irrigated. Obviously, we're looking at agricultural areas, but we want areas that are not impacted by human activities such as irrigation. So we're looking at natural conditions. We would like to look at areas that have benchmark soils, so tie in the sites that we're measuring with the major benchmark soils, as well as areas that represent different climatic regions, which are the major land resource areas. So we have a good distribution of information that's coming in. The station should also, as I mentioned, represent agricultural areas, and this doesn't have to be croplands. The first thing we often think about with agriculture is row crops, croplands, but this also includes areas of pasture, range, and timber. So we're trying to encompass a variety of agricultural land uses. And obviously, one of the things that we do have a concern about is station security, and I mentioned about having it on government lands, but more importantly is having these in areas where we feel that there'd be a lower chance of things such as vandalism, human impacts on the sites, just out of curiosity, just people that are around the sites. We'd like to keep these things secure. Uh, for a number of reasons. One is for the data collection itself, not to have any interference, and second is just for the equipment, the batteries, the solar panels, etc., so that there isn't vandalism. And we also try to focus on areas that are susceptible to drought, because again, we're trying to use this to assess drought and potentially as a tool for drought mitigation. So therefore, we're looking at areas that are susceptible. So the sites themselves, what do we use? We have The hydroprobe SDI-12s are currently what we use for our measurements in the soil moisture and soil temperature. And as I mentioned, these are installed at those 5 depths. But before we do this, we want to do a good soil description, a characterization of the site, because really understanding the medium that the water moves through and is held in is critical for understanding then the soil moisture itself. It's not just a uniform structure, but it has a lot of horizons, a lot of variations. And so we want to make sure that we map that and that we categorize that for each of the sites. And that information, these characterizations, are available on our webpage. So the first thing we do before we install the sensors is to map the soils. And that's one of the reasons we work closely with soil scientists to make sure that we have that expertise in the field, that we are tying in the climate and soil information with the soil profile itself, with the soil characteristics of the site. The soil sensors then are installed we install a hole for the 4 upper sensors. The deepest sensor is a separate hole that is installed at 1 meter deep, that we install that one vertically. So we'll drill a hole and we will install the sensor down into the soils at 1 meter. And we try to keep that hole really small so there's less chance of water moving down the borehole where we put the sensor. And we try to seal it off above. Also, there's less disturbance this way of the soils that were made. The other sensors are going into the hole next to that, where the deep 1 meter sensor is. And these are dispersed around the hole in different locations. So they're not all in a vertical line. We install these at and dispersion around the small holes, so there's less interference from each other, both in the compaction of the soils as well as water transport disturbing the soils. The less you disturb the soils, the better. So we take real care not to compact the soils as we put the sensors in, and to try to keep the area as undisturbed as possible, so that we're measuring the true hydrology. And on the wires themselves, we actually run the wires opposite of where the sensor is put in, so across the hole, so that we can put in a drip loop, so that water doesn't run down the wires, which if water was to condensate or collect onto the wires, if it ran down the wires into the sensor, then of course it would alter the measurements of the soil moisture. So we put in a drip loop to minimize that impact. And then the wires are all put into a flex conduit, which is then buried from the sensor site over to where our tower is for the scan site, buried under the ground to help protect it. But certainly the conduit is another part of the protection for that, and we seal that. So about the scan stations themselves, approval for these stations comes through NRCS. And so the stations that we currently have, the majority of these stations were installed by NRCS with funds made available to us, and then are operated by us. And the decision on where these sites are located and to approve the sites is with the National Water and Climate Center. And we don't always incorporate, we have, but we don't always incorporate other stations outside of the SCAN network into our network. Unless it meets certain criteria. And those criteria have to be things such as that the installation process was similar to ours, so that it's the same setup, that they use compatible or the same sensors that we use. And so we're trying to, again, to look at consistency in the network. And so we don't have a lot of variations from site to site, that the sites are comparable, so that we have a system that is that has the same qualifications across the country. And with any of these installations that we put in, either through NRCS or through outside groups, it's essential that we secure funding for the maintenance, because it's not something that you just put in a station and then walk away and it collects information. These stations do require maintenance. They do require upgrades, sensors, calibrations, many aspects that is a necessity to have this maintenance. And so we require if we were to bring in stations from outside of the SCAN network into the network, or to install new stations, that they come with at least 10 years of funding for the maintenance of the station. The National Water and Climate Center personnel, or those that we train in each of the states, those with the soil surveys or other folks, sometimes with universities, sometimes with other agencies, that we would train are those who are responsible for the operation and maintenance of these stations. Future plans right now are for us to work more closely with the Soil and Plant Science Division within NRCS, and because they have personnel located across the country. In fact, NRCS has offices in almost every county across the country. So we have personnel that are in close proximity to the SCAN stations, to each of those stations. And that would be a great assistance in having a timely response for when stations go down, having folks that can help us with the maintenance of those sites on an annual basis to reduce our travel and time. So there's many positive aspects to that. Those that are interested in installing sites in a state, the first step on that would be to contact the state conservationist within those states, or the director of the Pacific Islands or the Caribbean, and talk about putting together an agreement with them. It would be an agreement with each of the states to install a SCAN site, and then they would then contract through the National Water and Climate Center, our personnel, through us or either the Soil Survey Center, to be doing the maintenance at these sites. And with that, just a brief summary of the SCAN network, and I'll be happy to address any questions you have. Thank you.
Okay, so that was Mike Strobel, and Heather Hoffman is in the chat, or could speak up now if there are any questions. Otherwise, we can go on to our another network presentation and leave everything for the end, which is probably my preference, unless there's something burning out there. Question from Charlie: how close to the soil sensor installation holes do you dig your soil pit for a soil description? Heather, do you have an answer for that?
Hi everyone, this is Heather. I just wanted to let you know that we do have several folks from the National Water and Climate Center SCAN team on the line to answer the questions. So given they're the experts for the operations, I'll pass it on to Kent or Alex to answer the question.
Yeah, Mike, I can answer that. This is
Okay.
Kent Sutcliffe with NRCS. They're pretty closely located. It depends on the site and the site conditions, obviously, but we try to sync up the same horizons, make sure we've got the same horizons described as we have the sensors installed in.
Okay. From my understanding, and I've seen this, the PET-ON information is published at the websites, the SCAN website, and it's available for every station, most every station. I'll take that back. There may be a few of the add-on stations that maybe they're not quite up to date on.
Right, it would be
Utah.
most, for
Utah.
sure.
Okay, I'm gonna move on next to Pam. Pam, are you ready?
Mike, before she does that, can I just mention out loud and also
Sure.
chat, but just for folks, the SCAN folks, there are a number of other questions that came through. If you could just be in the chat box, if you could open that up and look through those and give answers as we go, that'd be great.
Okay.
All right, I'm ready. Can you hear me?
Yes, I can.
All righty, let's jump right in then. I'm Pam Knox. I'm the director of the University of Georgia Weather Network. You can see a map here of most of our stations. There's been a couple additions since this map was made. I haven't had a chance to update it. Georgia is a pretty big state. We have a big coastal plain and a lot of commercial agriculture goes on there. That would be more in the green, the lower elevation. We also do have an uplands, Piedmont area and some mountains up in the Northeast. And things up there are more like apples and other things, that grapes that grow in cooler weather. So we have quite a variety. Georgia's #1 part of the economy is agriculture. And so that's something that's really important. And I see my screen is not, there we go. Never seems to behave when you want it to, does it? Our stations were first put in on June 1st, 1991. So we're just coming up on 30 years. It was put in by Dr. Gert Hogenboom, who worked for a while with the Mesonet out in Washington State. And he just put stations in wherever he could. He had a patchwork of funding. So he started off with about 6 stations on university sites. By 2000, there were 37 stations, and now we're up to 87 stations in Georgia, and we have 1 legacy site at an old UGA facility in Costa Rica. The latest one we added was in October of last year at Glenville, which is sort of halfway between Vidalia and the coast. Wanted to mention that Georgia was one of the original participants in the National Mesonet program from 2005 to 2006, which was started by the National Weather Service as sort of a pilot program to figure out whether or not they could do a Mesonet program across the whole country. And so we were one of the earliest states to get involved with that. You might ask, well, why did they want to do that? It's because of situations like the one here shown in the picture, where you have a plot of ground with 3 or 4 different weather stations all lined up next to each other, collecting different kinds of information. And it really seems pretty silly. When I was a state climatologist in Wisconsin, there was one airport up in Rhinelander, which is in northern Wisconsin, that had 5 different stations lined up along the runway. One was owned by forestry, one was owned by the university, one was an AWAS system, and so on. And it was just ridiculous. And so they were really trying to avoid a lot of this duplication and get the best bang for the buck, if you will. So when we were doing that project, we started out with a grid map like this, which the grids were 20 by 20 miles. And we identified all the potential stations where we could put a weather station, thinking that we'd rather put one in a place there already was some information and some ownership. And so we had a committee that looked at all these sites and sort of made a judgment about which ones would be the best places to look. And in the summer of 2005, I had 4 students that went out across the state and surveyed all these sites. They filled out a big form and that had information about siting, the kind of soil, how close were the nearest trees and so on. And we did all this, and then the committees looked at all the surveys and picked out which were the best sites in each of those grids. We did about 3/4 of the state that summer, and we were still working at it when the program got shut down by the National Weather Service. And I don't know anything about the politics of that, but now they contract instead, and we are one of the beneficiaries of getting that contract. That's one of our biggest sources of funding. So just to give you a rough idea of what our funding is like for those 87 stations, our total budget is roughly $400,000. Varies somewhat from year to year, depending on whether we have to buy new trucks or not. The biggest sources of funding are the contract from the National Weather Service to put our weather data into MADIS. That's run through synoptic data. And the University of Georgia also has hard money for 3 full-time positions, but we have no operating funds for the network from the university or from the state for that matter. We also get a bunch of funding from commodity groups like cotton and peanuts. They pay $5,000 per year to help support the network. That was really critical because a few years ago, before the Weather Service was buying our data, we almost went under because we had really no funding except for those 3 positions. Now we have enough extra funding, so we have a full-time quality control person and another half-time maintenance staff. We are down 1 person. We lost our web programmer right before the pandemic, and then the university went into a hiring freeze. If you want to try to hire anybody over $40,000 a year, you got to go through a huge amount of paperwork, and we have not successfully done that yet. And so we're waiting to get a web programmer to help us. We really take pride in our visit record for our stations. Most of the stations are visited once a month. Eddie likes to drive. He's the guy there in the UGA shirt, and he spends pretty much full time on the road. He does come in on Mondays to do calibrations and set up his schedule for the week. But he and Dennis, who's the halftime technician there on the left, maintain all those stations. Grass grows a long time in Georgia, and so they go out and do a lot of mowing. Some of the local people mow, but they're not very good about avoiding the wires that go into the ground. And so we usually prefer to do it ourselves. And then we have all that data comes in and is flagged, and our data quality expert gets a list every day of things that have been flagged, like if our 2 precipitation gauges read different amounts, more than a certain amount different, has to go in and look at all those and checks the radar and so on. And he corrects that. During the pandemic, Dennis was not allowed to work. He's 75 years old, and they told him it was too risky for him. So Eddie had to do all that himself. I think the visits went down a little bit, but we kept going all the way through the pandemic, and we did not have any loss of data. And I think the producers were very pleased with that. This is a typical one of our stations. It's all pretty much Campbell Scientific equipment. I think the pyranometer might be something different. And this one happens to show an evaporation pan. We don't use that. It just happened to be on that site. All the usual suite of instruments. Our soil moisture sensor is an older one. It's a CS650, which measures an integrated water in the top 12 inches of the ground. We have been asked to go to having more than one sensor, but it's really hard with a limited number of people to start changing things. And we have made the choice to try to keep our equipment standard between all the different 87 stations, because it's a lot easier to maintain, even though we do get asked from time to time to add extra sensors, like, for example, leaf wetness sensors. We have chosen not to do that. And, in the long run, I think it'd be nice to add taller towers, but you need more people to maintain those towers. And so far we have not done that. We also have a number of calculations that are done. A lot of these are pretty standard things that I'm sure most of you have: degree days, chill hours for peaches and blueberries, water balance, some irrigation scheduling apps. And we have a project that was done by some of the agricultural engineers of predicting minimum temperatures. And that was used, especially used this time of year for blueberries, because they use irrigation to do frost protection. Like, they had some frost this morning. They turn on the water, and that protects the blueberry blooms. And so they don't have a reduction in yield due to the frost. And so we did have some work done on that as well. The communications that we do now are all done via Verizon cell modem. And when we started, it was hard phone lines, and those are pretty expensive, especially when you're running them out way out into rural locations. And so our communications bills have come down quite a bit by switching to Verizon. Occasionally we do have problems with the Verizon network, but overall it's been really reliable. We access the data every 15 minutes, and that will give an estimate of what the highest and lowest temperature were like during that 15 minutes, the average wind speed and the gust, and all the other associated variables that we get from our suite of instruments. It's collected right now on a server, and we're also storing it on Amazon Web Services. Our goal is to move to Amazon Web Services, but until we get a web programmer, we're kind of stuck in the middle. And so we've been keeping the website linked to the local server, but we do plan to upgrade to a direct link as soon as we get a web programmer up to speed. We do not make most of our data available to the public because we need to sell the data to help support us. So we have historical high and low temperature and daily precipitation available. Anything else other than current data, they pretty much have to come to us. And we do provide a lot of it for free, especially to university researchers, but we do sell the data as well to help support the network. We have some plans to improve things. We're going to add a couple of stations, one near Columbus on the west central part of the state, and one near Gray, Georgia. And those are just to fill a couple of relatively big holes in the network. We probably are going to remove a couple of really bad stations. We have one up in Alpharetta that's right next to a building. It was the only place that the golf course would let us put it. It's really bad because they've had a couple of trees grow up around it. And so that one will be moved sometime in this year, I think. Of course, we need to hire the web programmer to help us update that. And, as you know, when you try to update a website, the people that are using it now have to have access to it. So you have to create a new website sort of on the side and test out all the bugs before you can switch it over. And we have a long list of corrections we need to make, and we have a bunch of new calculators that we want to add, such things as an accumulation of solar radiation for the corn producers. Another thing I have to do is fend off my dean, who wants to put cheap stations everywhere. And she says, well, more data is better. And I said, well, bad data is worse than no data at all. And so, and we can't sell the data from the cheap stations to synoptic data. And so far we've been able to fend that off. And also we've got almost 30 years of data. So we're going to start working on creating climate summaries. And I have some money for some students at the University of Georgia who now has an atmospheric sciences program to do some of that work. Just wanted to kind of end this with a high and low. The left picture is our station at Donaldsonville, Georgia, the day after Hurricane Michael went through. It was in the eye wall. They had a peak gust of 115 miles per hour. And you can see there's some loose cables on there. And if you look hard, you'll see that the solar panel is gone, but everything else worked properly. And it was an amazing thing to see that happen. So that's really a high point of that particular station. And then probably the low point is the picture on the right, which is a picture of our Gainesville, Georgia station 2 years ago, almost exactly 2 years ago. It's located next to Lake Lanier, which is a big reservoir which provides water to Atlanta. But you can see they set record high levels for the lake, and it inundated our station, which was probably a little too close to the lake. I'm sure our soil moisture and soil temperature values were not very accurate. I think one of the precip gauges also got breached, but the rest of the station worked fine. And so siting, as always, is important, and you got to think about not only what's happening today, but also what might happen in the future. So that's all I've got for our station network, and happy to answer questions. I see there's a bunch in chat, but I can't see it when I'm showing my screen. So I'm going to get out of that and happy to answer questions.
Thanks, Pam. Most of those questions still seem to be scan questions right now, so you're safe.
Okay, good.
And if folks don't mind, I'm going to move on to Nathan. Nathan, are you ready? Hopefully, I did not see a presentation in an email from you, so whew, thank goodness. So this is Nathan Edwards from South Dakota State, who will be presenting, and then we'll get into some more general questions after.
All right. Instead of talking about our state in particular, I'm going to talk about the Upper Missouri River Basin Project, which is a collaboration under the Army Corps of Engineers with 5 state mesonettes. And anyway, here we go. This is the area of concern of the project. It's the Upper Missouri River Basin that's upstream of Sioux City, Iowa, everything below 5,500 feet. This was triggered by flooding in 2011. The project is headed up by the Army Corps of Engineers, and the funding comes through them. It involves, like I said, 5 state mesonettes, all based at universities. It involves NOAA, in particular the River Forecast Center and the SMNOW modelers. It also involves NRCS doing soil sampling. This is the first station that was installed in the basin. There's much more on it that I didn't label here that's related to the snow gathering. But what's important for purposes for soil moisture monitoring is in particular the being able to have all the values needed to calculate Penman-Monteith evapotranspiration and also precipitation. Of course, we've also got the soil moisture sensors. This is the common profile. We do volumetric water content and temperature. All of the stations are being sampled by the NRCS. So on the left there, you can see the state mesonette station. And right in front of you, you can see the trench where it's being sampled. And all of that is going off to the Kellogg lab for analysis. This is being evaluated as a pilot for the nation. The model is 1 station per 500 square miles. It places stations not just in places that are well suited to get things like temperature and wind, but also for representative soil. And all of the sites are characterized for soil, like I mentioned. We'll all be instrumented to be able to calculate evapotranspiration, potential evapotranspiration and precipitation. And the model also involves the working together of state and federal partners. And the way that it works monetarily is to provide funding on an ongoing basis via data purchase. And basically there is legislation in place that calls for the evaluation of this as a model nationally, which is mentions the National Coordinated Soil Moisture Monitoring Network by name. I guess we're doing questions all together, so I'll just wrap it up right there.
Thank you, Nathan. And I'll start back. I think the most recent question was for you. What soils analyses is Kellogg Lab doing as a part of this initiative?
So the answer to that question, so they do like the full suite of stuff. Not all of it, which is necessary for this project, I believe, but I mean, the main stuff that we're looking at getting out of it is the stuff needed for the retention curve. And then, specifically what it is it's an 80-inch pit, provided that they can get that deep based on what the water table is or bedrock. And then they do the full suite though that Kellogg does. If I tried to answer that comprehensively, I would be outside of my area of expertise, and I would take up too much time.
I think, and they are funded to do that, and as well come out and do the soil profiling through this project. They've also expressed an interest in ability to, in the background, which means it's not an urgent priority for them, but Kellogg has offered for any soil moisture network stations, this is from anywhere in the US, to run analysis for a simple set of criteria: sand, silt, clay, bulk density, if possible, with cluster analysis, with clump analysis, and things like that. But they would basically, they wouldn't be able to come out and get it. You have to send them the cores, and they would run analysis for you when they have the time, quote unquote. So, question from Jerry Brodsky, New York State Mesonet. Do you recommend cutting the grass over the soil sensor area, or is it best to leave uncut? How do your stations handle this? Pam mentioned they do a lot of mowing.
We have a pretty small profile for where the cords go into the ground for our soil measurements. So they try to cut around it, but they try not to cut the wires. They have enough problems already with rodents, so they don't really want to make it worse.
You, Nathan?
I think there's an argument to leaving it uncut, at least over that plot. It might need to be cut other places for other reasons around the station, but that's what we're planning on doing, is leaving it uncut in that plot.
Now, for many of your stations, Nathan, you have a lot of natural or rangeland. Is that accurate?
Yeah. So, I mean, basically, now you're talking about within South Dakota or within the basin?
We'll say South Dakota in this case.
Yeah, so in South Dakota, I mean, typically what you're talking about is largely row crops in the east and largely rangeland in the west. I mean, you get farther west, there's no grass at all. So you just go with natural cover, which is, like sagebrush for some of it, so.
And I'll point out that for, say, a site network like Neon, they're particularly not maintaining the sites over those sensors. They're natural environments, so they're leaving as whatever grows. They're trying to not disturb even on the installation. So Bruce Baker asks, how did the Missouri Basin Project come up with the spatial resolution for a national network? This may have several answers. Nathan, do you have any insight? Or Kevin Grody, I thought was on the line as well.
So I think basically where we started off with that was it evolved. Actually, I don't know. Kevin, would you prefer to explain that, or? I don't know, maybe.
Can you hear me?
Yeah, we can hear you now.
Okay. Yeah, so it was a process for us to figure out what kind of distribution we're looking at, because as Nathan mentioned in one of his slides, the area in question for the plains area for the upper Missouri River Basin is 200, well, he said 265,000. One of my calculations came out to about 270,000. So we're kind of splitting hairs there. Bottom line is it's an enormous area. And when it comes to soil moisture and soil temperature, I think the distribution with our conversations with subject matter experts came out that we don't need to have one every 400, 500, or 600 square miles. We could probably get by with one every 1,200 square miles when it comes to identifying dominant soil types and being able to take soil moisture and soil temperature and integrate that into our runoff models. So really it came down to what kind of distribution do we need for the plains snow aspect of it? What kind of information do we need, and how spaced do the sites need to be for the snow information to be collected and then integrated into the Missouri Basin River Forecast Center's Snow 17 model, as well as the SNODAS model that No Risk is working on. And that's how we sort of landed on 500 square miles. And then it comes out to about 540 or so sites total in the upper Missouri Basin. Over.
Okay, that's useful information. There's always been numbers thrown about in the past. At one point, there was a calculation of we need 10,000 stations in the U.S. To adequately, and that was 10,000, or was it 10,035? Like, where does that number come from? Well, they just, significant digits there, resulting in that number being that large. Certainly things that control, and this can be part of the siting discussion later, soil diversity, landscape diversity, topography, all feed into decisions locally. It's not one gridding resolution that dictates that siting density. It's also, and part of this session is about why does the network exist? And I'm going to jump in front of the line and ask my question to Pam first, then Nathan. Why does your network exist? Who said we need this?
Well, for Georgia, Gert was involved heavily in decision support, statistics and so on, and he needed data to support that, and he couldn't get enough data from Weather Service sites. He needed to have agriculturally important variables, and so he set up his network so that he could work his decision support tools into that, and he still uses our network. He's down in Florida now, so that is the reason that he started, and have just kept it going for all these years through several directors.
So ag's a prime driver there, Nathan?
It is.
Yeah, I mean, so I would say probably ours, it'd be fair to say that ours was tied to ag research at locations. I mean, the station that I showed there started out as a manual station in the 1800s. And it was kept, I mean, it predates statehood, it predates, the co-op program, all that kind of thing. But it was to support ag research primarily. And then as they became automated, that was, again, the issue, the motivating driver. And then as we put them more places, and made that available to the public in the advent of the web and stuff like that. I mean, it, you know, and the data became live. That all of that changed, like how the network evolved. But agriculture is a big one, and of course flooding is I mean, since 2011. And I would say that's not just for South Dakota. There's about 140 soil moisture network stations run by the 5 state mesonettes in the upper Missouri River Basin. And that was a great building point, which fueled the UMRB network.
Thank you, Nathan. And I'll speak for SCAN on this one a little bit. Early SNOWTEL. SNOWTEL is a network monitoring snow. And so agriculture is less tied to that. It's more water supply and water storage and quantity there, and adding sensors to that network. And then the rest of the SCAN network was kind of ad hoc development for specific questions. I think locally they'd like to have a nationally supported station at a local location, maybe one station in a state sometimes. Or there's densities, especially in the Mississippi River Delta down in Louisiana, Arkansas, and Mississippi had a density of stations put in because of flooding, I think. And then Utah and Alabama had other specific investments during particular projects, not necessarily agriculture. If there are still questions popping through in the chat, and I thank the speakers for replying to them, I want to keep myself honest. We're at 12:52, and I said we'd take a 10-minute break before our next section. So I'm going to give everybody a chance to step away. Please continue answering questions if you can, and we'll see everybody back at 1 p.m. Eastern. Thank you.